Hello, I'm Aurelie Boisbunon, and I'm going to present you a novel symbolic regression algorithm called Zoetrope Genetic Programming, or ZGP for short. This is a joint work with my colleagues from My Data Models and INRIA. So I will start with some basics about symbolic regression. In this work, we focused on regression where we have the output variable y taking values, continuous values, and we wish to model its relationship with the input variables x and minimize its mean squared error to get the best model. So the choice of models that we can have depends on various options depending on what we need: performance, interpretability, size of data, training time, etc. And often we can see these graphs of interpretability versus performance, where we show how well these different models perform with respect to each criterion. But on those graphs, there is one that is usually missing, which is symbolic regression. So symbolic regression consists in looking at searching for models that can be expressed through a mathematical formula, like here, and they are usually represented through an expression tree that I show on the left. But since it involves the search for operators such as logarithm, square root, sinus, additions, etc., the search space is very large and it cannot be solved through standard machine learning techniques. However, it is a good trade-off between interpretability and flexibility because it allows to search for models that are more complicated than linear ones, but still interpretable. And they are particularly good when we have a small number of observations, on the contrary to deep neural network. But the question is, what about their performance in terms of accuracy and speed of training? So recently, there has been some benchmarks in the literature of symbolic regression, and especially I will cite here the one by Orzechowski et al. So this is a graph that I took from their work, in which they compared symbolic regression algorithms here on the left with traditional machine learning ones. And what we can see on this graph is that the best performance they could obtain was by augmenting a lot either the population size or the number of iterations, which result in a low in a very low speed for training. So this might be an issue as symbolic regression algorithms are already slower than more traditional machine learning ones. So this is the context in which we developed Zoetrope Genetic Programming. The term zoetrope comes from this device that is an ancestor of the camera, and consists in images that are inside a wheel, and when we make the wheel turn, it looks like it's moving. So one particular aspect of ZGP lies in the representation of its individuals. We can still represent it as a tree, but we will show it in a different way here. So the first step is to pick at random variables from the input variables here and or constants, and to keep them in memory in a set of elements. Then we combine we combine couples of these elements through fusion operations. So it's more complicated than just looking at operators and transforming them by operators. And we require several components here for the fusions. We have two operators here. We need to pick at random two, and they are combined through convex combination. So there is a real number here that we pick at random too. And finally, we decide whether the result of this operation is going to, through a Boolean, is going to be in E1 prime or E2 prime, and the other will be the same as E1 or E2, depending on what we chose. Then we repeat for the other couples of the other elements from the set. And if this number of elements is odd, we couple the last element of the set with the first element that was generated. And we repeat this process several times, which allows us to bound the complexity and avoids bloating. So at the end of these maturation steps, we obtain elements that we call zoetropes, and these zoetropes actually correspond to branches of the tree, or they can also be seen as new features. And finally, the last step consists in combining those zoetropes through elastic net, which allows us to both select the most relevant zoetropes, and also to find out, to optimize the weight of the remaining zoetropes. So in the end, what we have is a genotype that consists in the elements that we picked at the beginning, and the fusion operations and how they are defined through operators, a real number, and a Boolean. So now that we explained the representation of individuals, obviously, like in standard genetic programming, we will start with generating a number of individuals, and then we will iterate through mutation and crossover. So the mutation and crossover in the GP are also non-standard. First, the mutation relies on point mutation, where we randomly perturb either an element or fusion. So if it's an element, it's like in standard point mutation. But if it's a fusion, we replace one component among the fusion. But then what is non-standard in ZGP is that instead of just mutating one individual, we are considering couples of individuals. And we have two regimes. In the first regime, we will mutate the fittest of the two elements and replace the weakest or the worst by the mutant that was generated. And in the second regime, we mutate both elements, both individuals in the couple, and we replace each of them, but only if the fitness is improved. So with these two regimes, we are enabling exploration and exploitation at the same time. And the choice for each regime depends on the number of mutations that the best individuals already went through. Next, for crossover, we start by selecting a number of individuals, and among those individuals, we define which one is the fittest and which one is the weakest, and those will be the parents for crossover. Then we combine them by selecting at random elements and fusions from each of the parent. And finally, the offspring replaces the worst parent. And we repeat this process over different groups of individuals. So this was a presentation of how the GP works. Now we are going to compare it with the state of the art. So in order to do so, we were inspired by the benchmark performed by Ozeshevsky et al. So it's really similar to it. We considered the same database, which is Penn Machine Learning Benchmark. It consists of about 100 datasets in regression with less than 3,000 observations. And we compare with the same algorithm in symbolic regression and traditional machine learning algorithms. But we added obviously the GP and also a more recent symbolic regression one, which is FIT. So here are the results in terms of performance in R2 on the top here, or in normalized root mean squared error on the bottom here. The symbolic regression algorithms are marked by a star. And what we can see from these graphs is that there are 4 algorithms that are clearly above the others. First, we have gradient boosting, and then we have equivalence between random forest, fit, and the GP. So we have very good performance of two symbolic regression algorithms compared with random forest, which is really great. Then let's look at the performance versus training time, because in symbolic regression, it's often an issue. As I mentioned before, they are often slower than traditional machine learning ones. So here, what we want to look at is to find an algorithm that is both accurate, that has good performance, but takes the lowest computational time. I'm only showing the results for symbolic regression for clarity and also because they are still slower. But what we can see here is that the GP in blue is in the top left corner, which means it's the one that got the best results in both criteria. So high performance and low computational time. Fit and MRGP are close by, but they require to be parameterized for the computational time. By default, I think they take around 10 minutes. So we need to know in advance which would be a good time to get good performance. And GSGP is the fastest of all, but it's not very accurate, and especially it tends to build trees that are exponentially growing, so the interpretability is almost impossible with those. So if I go back to the graph of interpretability versus performance and plot the values of the algorithms we had in the benchmark, here I defined the performance with R2, and the interpretability as the number of nodes in the tree or the number of non-zero coefficients for linear models. So for traditional machine learning algorithms in black, it's mostly what we showed at the beginning. And for symbolic regression, we have some of them that are similar, but the most interesting feature is that we have the 3 best symbolic regression algorithms that are much more interpretable than random forest, almost as accurate or as accurate, but much more interpretable. And this is a really nice feature. CGP is a bit less interpretable than the other 2, and this comes mostly from the fusion of operators, but we are looking into ways to improve it, and I think we can manage to be even more interpretable. So this concludes my talk. I presented you our novel symbolic regression algorithm, ZGP, with a novel representation of how the trees are built, and it allows both feature construction, efficiency, good performance, and some kind of smoothness in the search space. The variation operators are also specific to the GP, and they allow to improve the fitness at each step. And we got very good performance with good computational time. I'd like to mention that the GP is embedded in a commercial tool, but the public version will be available soon to the community. So finally, as I mentioned before, we are working on improving the complexity of the models generated by the GP. And we are also looking at seeing how it compares with state of the art in classification, because it also can be used in classification. And finally, I'd like to mention that in classification in particular, we applied it in a semi-supervised context with a pre-processing step for labelization. And we got very good results for application in time series, especially for motor failure detection. So thank you for your attention, and I would be very happy to answer any question you have.